morning, everybody. Hope you're all healthy and safe. We are going to continue with our section on Laplace transforms. So, in the previous lecture, we had introduced what was Laplace transform and what we had discussed in detail the linearity of Laplace transform. So now this the Laplace transform. Now, if you just think about it, the Laplace transform, it need not exist for every function that we are given. Okay, so for some functions, the Laplace transform does not exist because we have defined the Laplace transform in terms of integral, right? That is integral from 0 to infinity. So it is not a definite value. It is going like infinity. So if that integral converges to a point, then that would be the Laplace transform. Okay, so there might be cases when the integral does not converge. Okay, that is, we cannot find the converging means what it should come closer to a point, a particular point. That is, we can find a particular value, but if it is not converging, then we cannot find a particular value. It will be going to infinity. Okay, so because of the definition of Laplace transform itself, there might be cases in which some functions, for some functions, the Laplace transform cannot be determined. So there is actually a sufficient condition for the Laplace transform to exist. So let's just look into that today in today's class. So the sufficient condition for existence of the transform, that is, if f of t is piecewise continuous on the interval 0 infinity and of exponential order, then the Laplace transform of f of t exists for s greater than c, where c is any arbitrary point. So we know we define Laplace transform for any particular intervals only, like s greater than. So you have seen L of e raised to 3t exists for s greater than -3 and so on. We have done that in the previous lectures. So the sufficient condition is actually, there are basically two conditions. One is that the function that we are considering, whose Laplace transform we have to find, it must be piecewise continuous. Now we are all familiar with piecewise continuous. That is, if you are choosing a particular interval AB from A to C, it will be having a particular value which is continuous, and from C to B it will have some other particular value, like it is like a step function. It forms step function or some other, not necessarily step function is an example of a piecewise continuous function. So f of t must be piecewise continuous. That is, in the given interval, if you take any particular sub-intervals, and all those sub-intervals, the function must be continuous, but altogether in that particular interval it need not be continuous. So the function must be piecewise continuous and it must be of exponential order. So we shall discuss what is meant by exponential order in detail. If these two conditions are satisfied, then the Laplace transform of that particular function exists for s greater than c. Okay, so let's understand what is meant by exponential order. So a function f is said to be of exponential order if there exists constants c, capital M, both greater than 0, and capital T greater than 0, such that the modulus of f of t will be less than or equal to m into e raised to ct for all t greater than or equal to capital T. This is the definition of exponential order. So a function is said to be of exponential order if its modulus value is less than or equal to some m into exponent. It is related to the exponential function, right? So it is less than or equal to m into e raised to ct for all t greater than or equal to tc. Or we can say that if you look at the graphs of f and e, this graph should move slowly than exponential graph. Okay, so that is, it will tend to infinity in a slower pace than the exponential function. Such functions are called as such functions are said to be of exponential order. That is, if a function graphically, I'm telling, the precise definition is in this manner: modulus must be less than m into e raised to ct. Graphically, the graph of the function should tend to infinity in a slower pace than the graph of the exponential function. So this is what is meant by exponential order. Now if you see let's just see some functions. So all the functions need not be of exponential order or piecewise continuous. So these are the cases when the Laplace transform will not exist. So we'll just see few examples of the functions which have exponential order and which do not have exponential order. So if you consider f of t is equal to, say, t, then now for c is equal to 1, okay, we have t is less than e raised to t. That is clearly trivial. It is a trivial function. Modulus of t will be less than e raised to t. Okay, and if you see the graph also, what is the graph of exponential function? It goes like this, right? And what is the graph of t? It is a straight line. So e raised to t tends to infinity in a faster pace more quickly than the f of t that we have considered. Okay, this is similar. Some other functions are like f of t is equal to e raised to minus t. These and all are examples of functions which are of exponential order. Okay, now if you look at the function f of t is equal to e raised to t square. So instead of comparing, if I just see, let us consider the integral. Okay, integral say 0 to infinity, we'll have e raised to minus st into e raised to t square into dt. This will be the Laplace transform of this particular function, right? L of e raised to t square is equal to this. Now as t tends to infinity, what happens is e raised to minus st tends to 0, but e raised to t square will tend to infinity in a much faster pace. So there is a graph. You can see that this will be the graph of e raised to t. Okay, so e raised to minus st must be somewhat in this form only, depending on the value of s, but the value of e raised to t square is something like this. This is e raised to t square. So here you can see that e raised to t square is moving at a faster pace than e raised to t. It is tending to infinity in a much faster pace. So this will actually tend to infinity. So this integral will not converge. So the value of the Laplace transform cannot be determined. Okay, so these are few examples of functions which have exponential order and which do not have exponential order, and I hope the concept of piecewise continuity is clear for you guys. So now what we'll do is we are going to prove the sufficient condition. Okay, the condition is f of t is piecewise continuous and of exponential order, right? So these are the two conditions that we have to consider, and then this implies L of, that is the Laplace transform of f of t, exists for s greater than c. Okay, so let us see the proof we have. It is the Laplace transform of f of t is nothing but integral 0 to infinity e raised to minus st into f of t dt. Okay, now I can write this as integral 0 to t e raised to minus st into f of t dt plus integral from t to infinity e raised to minus st into f of t. So I am naming this as I1 plus I2, that is I am choosing any point t between the interval 0 and infinity and just splitting the integral. We know we are given the provision to do this. So in this, the Laplace transform of f of t is nothing but I1 plus I2. Now I1 is a definite integral, right? It is varying from 0 to t, okay, and the function is piecewise continuous. So there might be, we can find some interval in which this I1 will be existing. So it will be the sum of integrals over the intervals. It will be the sum of the integrals over the interval in which, over the interval on which the function e raised to minus st into f of t is continuous. Okay, so since the function is continuous, the integral will exist. Now it will be actually not complete, since the function is piecewise continuous, we can find some intervals in which the function is continuous, and we can find the integral value, and taking the sum of all these integral value from 0 to t, we will get the value of I1. Now in case of I2, what happens is, let's given that f is of exponential order, given f of t is of exponential order, right? So this implies what happens is there exists constants c m greater than 0 and t greater than 0 such that modulus of f of t will be less than or equal to m into e raised to ct for t greater than capital T. So this is the definition of exponential order, right? So let's see what happens to I2. Now I2 is nothing but integral from t to infinity e raised to minus st into f of t dt, right? So modulus of I2 will be equal to modulus integral t to infinity e raised to minus st into f of t into dt. By the modulus property, the modulus goes inside the integral, so we'll get a negative, inequality sign, less than or equal to integral t to infinity modulus of e raised to minus st into f of t into dt. Okay, now this e raised to minus st, and if you take the modulus of f of t, that is less than or equal to integral t to infinity e raised to minus st into m into e raised to ct into dt. Now this is nothing but m into integral t to infinity e raised to minus of s minus ct into dt. What is the integral of e raised to minus s minus t? That is nothing but integral value will be m into e raised to minus s minus c t by s minus c minus varying from t to infinity, right? So the first value, that is e raised to minus infinity, that is 0, and we'll get minus of, let me write down. So I2 will be equal to m into minus e raised to minus s minus c t by s minus c varying from t to infinity. So when it is infinity, it becomes e raised to minus infinity is 0, and we have minus of minus e raised to minus s minus c into capital T by s minus c. So this is nothing but e raised to minus s minus c into t by s minus c. So this integral always exists for s greater than c. Okay, that is we had just like I had mentioned before, if s is, this value must be positive. If s is, this s minus c is not positive, then we'll have e raised to some positive power of t. So when we apply t, when we tend it to infinity, it becomes e raised to infinity, and that becomes undefined. So s must be greater than c. So if the function is, therefore L of f of t exists for s greater than c. Okay, so because I1 is the sum of some particular integral and I2 has this particular value for s greater than c. So the Laplace transform of f of t exists. So this was a sufficient condition that we had to prove. Now we shall just see one more example and wind up this lecture. That is how to find the Laplace transform of a piecewise continuous function. That is, we need to find L of ft, okay, where f of t is given by 0 for 0 less than t less than 3 and 2 for t greater than equal to 3. Okay, so here what will be our capital T? Capital T will be 3. So L of f of t, or the Laplace transform of f of t, is nothing but, I am writing it directly, 0 to 3 e raised to minus st. What is the value from 0 to t of f of t? It is 0 plus 3 to infinity e raised to minus st into f of t. When t is greater than equal to 3, it becomes 2. So this is 0. Now plus 2 into, what is the integral of e raised to minus st? It is e raised to minus st by minus s varying from 3 to infinity. So this value becomes, first term is 0, second term negative into negative, it becomes positive. So this is e raised to minus 3s by s. Okay, so I hope the concept is clear. This is how we determine the Laplace transform of a piecewise continuous function which is given to us. So we have to take the corresponding t to be the point where the function breaks. Okay, so in that manner we can find the Laplace transform of a piecewise continuous function also. So these are the sufficient and condition for the Laplace transform to exist. That is, it must be of exponential order and the function must be piecewise continuous. So we shall do more problems related to this. So that's it for today's session. Thank you. Stay safe and stay healthy.